Hello and welcome to this video. In the last video we studied the insertion sort, and in this video we will study selection sort. So I did not give complexity calculation in the previous video, so in this video I'll refer to Donald Knuth's book. There is a topic of sorting by insertion on page number 91. Not really, I mean that is the PDF, it is on page 80. So the implementation of insertion sort in mix is given on page 81. So you can see this is the mix implementation, and the complexity calculations are given in these equations. And for best case, it would be order of n, and for worst case, it is order of n square. So these are the exact value of calculations. So you can refer to this. And now, since we are going to do selection sort, I will show you selection sort as well. So this is the selection sort program over here, and this is where the discussion start algorithm is given here, and we have the selection sort in mix, and the complexity calculations are given here. So like we are always interested in worst case for most programs. So worst case is order n square for the selection sort, and the average runtime is also n square. So it is slightly slower than insertion sort. So we now let's go and take a look at in selection sort algorithm. So as always, I have prepared two versions. One is the iterative version and another is recursive version. So we first look at the iterative version. So our driver program remains more or less same with the exception of the function name and the header name. The header is similar, and here we have our implementation. So let's see how it does it. So I have printed it, okay, the array, and then what it does is that it considers the entire array unsorted in the beginning. Okay, now what it will do is it will set minimum index to I. All right, now it takes the value of j as starting from 1, that is I plus 1. So I will be 0, so I plus 1 will be 1, and will continue to the rest of array. So you have basically divided the array in two parts. The first part is 1, and the second, that is the first element, and the second part is n minus 1 element. So array is divided into two. Now after that, what it does is it finds the minimum index. Okay, so if aj is less than a minimum index, then minimum index is j. All right, now it will go on till it finds some index which is less than that, and when that happens, it will swap both of them. So we'll see how it works out. So let's go to the folder, and we run gcc on this, and let's run this. You see, in the beginning, what will happen is this entire array is unsorted. All right, so this is the first print statement. Now I will be set as 0, so it is set as 0. So it will iterate on rest of the elements, and here you see minimum index is I. So is there any element which is less than 164? No. So this is the first run. After the first run, it will be remain the same. So this is this print statement. After that, I will become 1. So that is 384. Is there any element less than 384? That is 211. So 211 is put at its proper place, and 384 goes here because both are swapped. All right. Now I will be set to 3. So this will be, I believe, we have one print, second print, and third print. So this, okay. So in this case, it will take 705. I will become 2. So 705 it will take, and will find the minimum index on right hand side. So the minimum right hand side is 339. It will take 339 and swap with 705. After that, it will go on 592. On right hand side, it is 384. So 384 and 592 will be swapped. So that's how selection sort sorts the algorithm, sorts the array. Now we look at the recursive version. So main is kind of same, header is same. Let's look at the this. So in this case, the minimum index is found using a recursive algorithm over here. So if now the signature is a bit different, we need to pass an initial index that is 0. So when initial index is 0, we go on finding minimum index. Okay, so we set the initial index to n-1 here. All right, and initial index is 0. So 0 to n-1, we want to find the minimum index. So when I becomes equal to j, we return I. That is the minimum index is j in this case. All right. So after that, it finds the minimum of remaining indexes. Okay. So in this case, it increases I plus 1. That is, we have passed 0, it will become 1. And then j will remain same here. That is n-1. So it then compares the AK. So what will happen here is, let me try to explain a bit. It will not reach the next statement yet. So A1 and n-1 will be passed to minimum index again. So then it will become 2 and n-1 and so on till I is equal to n-1. In that case, even in the last statement, I will be n-1. So it will return and k will become n-1. Okay. Now what will happen is, this AK will be compared with AI. So when we loop back, it will be n-2. So it will compare n-2 with a n-1. And again, it will loop back and n-3 will be compared with the minimum of this function, this value, the previous value. And that's how it finds the minimum index. Now, if k is not equal to initial index, then it swaps. Okay. And after that, it will increase the initial index here and here, so that the array is split again, and you find the recursive selection sort here. So that's what happens. So let's see, if you want to understand this, I will just print that array. Not k, l. First we print, okay, we print this k also, and ID. So we are printing the array here, all of it. Not okay. Now we take this. That should do it. Okay, and we need to print after swap also. So that you can see this, how this works out. Okay. So now we compile the recursive version, and this is our main and our selection sort. And there is a print without f. So now let's see how the recursive one works out. So see, in the beginning, k will, okay, there is somewhere something wrong. I have made some mistake here. L is equal to 0, L less than n, and L. Why these values are garbage? Okay. Okay, I have not given space. The values are not garbage. You see, initially the array will be the original array and k will be 0. So since this is in order, that is 164, 385, 384 are in order, nothing will happen. Once it reaches, and you see index is 5. Once it reaches 384, it swaps it with 211 because 211 is less than this. So let's see which element is 211. So it is 0, 1, 2, 3, 4, 5. So k is 5 here. So when it goes to 384, that is our initial index is increased, okay, then this is replaced with 384. After that, initial index will be 705 and this will replace with 339, which is our 8th position. Once it has found 339, 592 will be exchanged with 384, which is our k is equal to 5. And so on it progresses till it terminates. So that's how selection sort is done in recursive algorithm. And I have already shown the complexity calculation of selection sort. So you will have to study Donald nodes in quite a bit of depth to understand that how it works. So with this, we come to the end of selection sort and insertion sort. In our next video, we will study one of the most important sorting algorithms, and that is quicksort. Quicksort is used at many places because of its fantastic properties on complexity, time requirement, and memory consumption, because space complexity of quicksort is O1. That is, it does not require extra memory to sort the array. Whenever you talk of quicksort, there is always merge sort comparison with quicksort because time complexities are same, but merge sort requires a lot more space than quicksort. But there is one extra property which merge sort has, is that it is stable sort, but quicksort is not stable. So stay tuned for my next video on quicksort, and I'll again refer to Donald Knuth's book on complexity calculation. So I hope you have found this video useful and informative, and if so, please subscribe to the channel and like the video. I'll see you in next video. Enjoy.